Welcome to the HVAC Matrix Drive Z1000U technical presentation, Merging Green and Technology. My name is Paul Avery, and I'm with HVAC's Technical Training Services Group. I will be leading you through this presentation that was originally presented by Ron Kaler from the HVAC Building Automation Group at the 2015 AHR Expo. Before we get started on the technical details of the Z1000U Matrix Drive, you may wonder what inspired HVAC to develop the innovative features that you will see within the Z1000U Drive. Over the last number of years, if you've been reading trade magazines or following industry news, you will have seen a lot of articles focused on energy savings, energy efficiency, and harmonic reduction. And more recently, there have been articles regarding high-performance buildings and energy savings that would allow owners to possibly qualify for credits or other incentives. In addition to industry news, we also took a look at third-party market research such as IMS. Back in 2011, IMS Research published a report specifically focused on low harmonic and regenerative drives. From a worldwide drive integrated harmonic solution perspective, you can see the top 3 applications expecting growth for this type of product are commercial HVAC, elevators and escalators, and water and wastewater. Looking at North America from a commercial HVAC perspective, IMS is projecting an annual growth rate of over 16% through 2015 for a drive-integrated harmonic solution. IMS Research is also projecting that an integrated low harmonic drive for commercial HVAC will grow faster than low harmonic filter solutions. These industry trends and the market research studies have led us to develop the Z1000U Matrix Drive. The Z1000U utilizes a direct AC to AC conversion, focusing on energy savings, energy efficiency, and improved power quality. The Z1000U Matrix Drive has these main attributes: low harmonics, improved power factor, greater efficiency, power regeneration, compact size, and expanded motor control for controlling an induction motor or a permanent magnet motor. To keep this e-learning module to a reasonable length, I'm going to focus on 3 of these key attributes, those being low harmonics, greater efficiency, and compact size. To set the stage on how the Matrix Drive works, let's first take a look at the most typical product for AC variable speed application, this being the simple AC variable frequency drive motor control. In this typical general purpose drive, AC power is converted to DC and then inverted back to AC. The AC to DC portion of the operation is mainly accomplished through a rectifier bridge with 6 diodes. The DC voltage is then stored in DC bus capacitors. Finally, the DC voltage is inverted back to AC through 6 IGBTs that can vary the voltage and frequency delivered to the motor. Here are a few advantages of a simple VFD. It offers very good displacement power factor. The overall package is compact, and it has been well documented that in many applications using a VFD will create energy savings versus a cross-the-line operation. The downside of the simple VFD control is that it offers poor input harmonics, which we will see shortly. Also, in applications with overhauling load conditions, regenerated power could cause nuisance overvoltage trips and may require a dynamic braking resistor to eliminate these overvoltage trips. Looking at matrix technology, the matrix technology is a direct AC to AC converter. This AC to AC conversion is accomplished by 9 bidirectional switches. Having these 9 bidirectional switches allows power to flow from the input directly to the output and from the output back to the input. The key advantage of the matrix drive over other low harmonic solutions, such as multi-pulse or active front ends, are improved power factor, lower input harmonics, and all within a compact size package. The Z1000U offers greater system efficiency. Plus, if your application has any regenerative operation, the Z1000U will further reduce your overall power consumption. The Z1000U Matrix is also priced very competitively against other low harmonic solutions. The downside of a matrix drive is that when compared to a general purpose VFD, the matrix drive does have a price premium and will be physically larger with a higher parts count. Let's begin our discussion of the Z1000U with the topic of low harmonics. Referring back to our simple VFD drive without a reactor, the current distortion is approximately 88% with a true power factor of 0.75. The most cost-effective and economical way to reduce current distortion is by simply adding an AC reactor or DC link choke. By adding this option, you can reduce the current distortion by over 50% from 88% to 33%. And you can also improve power factor from 0.75 to 0.9. However, this may not allow you to meet the levels set forth in IEEE 519. One of the more popular and traditional methods to meet the levels of IEEE 519 is to use an AC drive in a multi-pulse configuration, such as a 12-pulse or 18-pulse configuration. This configuration offers input current distortion ranging from 6 to 12%. You also gain an incremental improvement in power factor from 0.9 to 0.98. The Z1000U matrix drive provides input current distortion levels between 3 and 5% and has a power factor of 0.98 or better. Let's compare the Z1000U matrix drive with an 18-pulse configured package. During internal Yaskawa laboratory testing, at full speed and full load, the Z1000U matrix drive and the 18-pulse configuration can both meet the strictest levels of IEEE 519. However, as you reduce the speed, the Z1000U can still maintain these levels even at speeds as low as 65%, whereas the 18-pulse can only meet these levels at 90% speed and above. Even at 50%, the harmonic characteristics of the Z1000U are still very good at around 7% total harmonic current distortion. A unique feature available in the Z1000U matrix drive is a function we refer to as eco mode. To explain how the eco mode function works, let's look at a VFD in a bypass configuration. Typically, this configuration is only used for VFD backup purposes and not as a low harmonic solution. But in this example, during acceleration and deceleration, the motor is controlled by the VFD. Whenever the motor needs to run at or near the power supply frequency, however, the motor switches to across-the-line operation. Across-the-line operation generates negligible harmonic content. In order to switch the motor to across-the-line operation, additional circuitry like contactors and phase detectors are required. The Z1000U's eco mode works like a pass-through mode. The graph on the lower left illustrates how this function works. In this eco mode example, the Z1000U is programmed with a frequency reference of 57 Hz. The motor accelerates up to 57 Hz, and at 57 Hz, the Z1000U's output will begin to synchronize with the input. After a very short period of time, the output and the input will be synchronized, and the bidirectional switches will stop switching and just pass through the input power. The waveforms on the right are a comparison between the input waveforms and the output waveforms before and after eco mode. Because of the Z1000U eco mode, it is possible to further reduce your current total harmonic distortion to a range from 1.6% to 2.7% without adding any additional components. To summarize the harmonics performance, the Z1000U matrix is an integrated drive package with a current distortion ranging between 3 and 5% and an improved power factor of 0.98 or better. This performance allows you to meet the strictest levels of IEEE 519 and can possibly reduce your power supply capacity requirements. This all in a product that only requires 3 wires in and 3 wires out. The next key benefit of the Z1000U matrix drive is the improved efficiency. Let's compare the efficiency of the Z1000U to other low harmonic drive solutions. Here is a graph that has 5 curves. The first curve is a typical fan curve. The x-axis shows the output frequency, the y-axis shows the fan's output power requirements. The fan curve shows that as the speed is reduced, so is the load on the fan. The other 4 curves are efficiency curves. They use the right-hand y-axis and show how output frequency affects the efficiency. The top 2 curves are drive-only efficiency comparisons, and the bottom 2 are total efficiency curve comparisons. In both comparisons, the Z1000U has 3% greater efficiency than other low harmonic drive solutions. Next, let's compare the Z1000U matrix to an 18-pulse configuration. You can see at both full speed and full load, the Z1000U matrix offers a 3% improvement in efficiency over the 18-pulse configuration. As you reduce the speed, the Z1000U has a much greater efficiency delta than the 18-pulse configuration. The Z1000U matrix also offers the ability to monitor the energy demand at various stages. You can monitor the power output and regenerative power directly with the Z1000U matrix to determine total power consumption. You can also easily input your energy price into the Z1000U matrix to calculate the power consumption based on energy cost in dollars. Another key attribute for an installation is physical size. Let's compare the size of the Z1000U matrix to another low harmonic solution using an active front-end configuration. The active front-end configuration will need the simple VFD, plus an active front-end converter, plus filtering components such as capacitors and reactors. Everything necessary for the proper operation of the Z1000U is included in the Z1000U package. Because of this, installation requires only 3 wires in and 3 wires out, dramatically reducing installation and wiring time. The all-in-one Z1000U package reduces your wiring by 70%, from 20 wires down to 6 wires. By going with the Z1000U, you reduce the physical package size by 65%, reduce the overall weight by 81%, and reduce your power watts loss by 19%. The last slide compared the Z1000U to an active front-end package. Let's continue with our comparison of a Z1000U matrix versus an 18-pulse configuration. This slide shows an 18-pulse bypass package versus a Z1000U also in a bypass configuration. Please keep in mind that the images are not to scale. By replacing an 18-pulse configuration with a Z1000U matrix drive, you can reduce your used floor space by 65%, or you can reduce your used wall space by 50%. As a side note, the Z1000U matrix also includes line fuses within the integrated package. Our final graphic comparison brings all of our categories back and lays out the Z1000U versus both a simple VFD with an active front end and also a simple VFD with just an input reactor and a dynamic braking solution. Whatever the case, the Z1000U offers the lowest harmonics, best power factor, and greatest efficiency, along with power regeneration, a compact size package, and with expanded motor control for either an induction motor or a permanent magnet motor. Hopefully we've been able to justify the title of this e-learning module by proving that the Z1000U truly is the merging of green and technology.